our story. By the way, if you ask anyone who studied complex analysis, 10 years ago, and ask what the course was about, it will turn out that calculus of residues is the main thing people use and remember and so on. So it's just the course is organized in such a way that most important thing is last week. Good. So before we pass actually to the new material, let me recall a few things from last week. So we discussed zeros and isolated singularity. Functions. So in particular, what we will need and use and keep using is that if we have a holomorphic function in some domain G and f of z naught is 0, then two things happen. So for example, so one thing is that there exists a number n such that f of z is z minus z naught to the n g of z. G of z is holomorphic and is not 0. And moreover, there exists a disk around this node of some radius where, so for every point z there, g of z is not 0, and so f of z is not 0 in the punched one. So this means that so there's a principle zeros of holomorphic functions are isolated. So then also we discussed singularities. So f was holomorphic in G complement to one point A. Then possible cases. Either so f was defined as a holomorphic function on the whole G. So then z equals A is removable singularity. Or there exists n, basically f of z is 1 over z minus a to the n g of z, where g of z holomorphic in the whole G, and G of A is not 0. So this means that it's a pole. So pole of degree n. So it was formulated differently, and maybe I should write formulation from the book. So we introduce g of z, which is f of z times z minus a to the n. Then g of z is holomorphic. Good. So, and then otherwise, singularity is essential. now for such a holomorphic function defined outside one point in a domain, so we defined its Laurent series. So f of z is sum from f equals minus infinity to infinity cn z to the n. So we define in which sense the series converge. Also, we expressed Cn as some integrals. Some small disk around A, some radius. F of z is minus A to n plus 1 to the n. So, in particular, they are uniquely given by this point A. So today we start from the definition, which immediately extends this subject. So suppose we have such function which is holomorphic in a complement to a point. So it's an isolated singularity. Then we consider the series. So definition. The residue of f a, so denoted by. So this is just coefficient minus 1 in this Laurent series at this point. So then, since we already have this Cauchy type formula, this is 1 over 2 pi integral over this. It's a small disk. F of z. So if you substitute minus 1 here, there's nothing in denominator. So minus 1 plus 1 is 0. F of z is n. So remarks. So if f is holomorphic in the whole G, then of course the residue is 0. So removable singularity in particular means that the residue is 0. But it's not if and only if. So the opposite is not true. Sorry. So this series is, of course, centered at the point A, not at 0. Good. So the opposite is not true, and the example is here. You can take f of z to be 1 over z squared, and then it will have a pole of order 2 at 0, but no residue, for obvious reasons. Good. Now, there's a main theorem about residues. It's called Cauchy residue theorem. which basically sums up all Cauchy type formulas we know. So again, suppose f has isolated singularity at k, and G is simply connected. So suppose we have maybe I'll draw a picture here. So there's G, and in G we have a simple closed path, which we call gamma. And the book says that the word simple, closed, and positively oriented should be treated intuitively. So I just draw. So it's something like a circle going, say, counterclockwise. That's all I can say at this point, because proper definition of orientation requires more. So suppose there are some singular points for the function. So we know them a1, am. So, oh, sorry, it's defined. So we threw away more than 1 point. So all these points are inside the closed, so the inner side of the closed part. So gamma, simple closed path. Around, and this requires more formal knowledge than we have. Around all points. So then we have what we would expect if there was only 1 point. So then integral over this part of f of z to z equals just sum of residues of f at each point. So notice that if there are no points, it's Cauchy integral theorem, because then such integral would be equal to 0. If there's 1 point, it's the well-known formula. Wait. So let's prove it. So there are many ways to prove it. So one way would be to do something like this, but so I'll draw one way which explains in a way what's going on, but also I'll produce a formal proof a bit later. So one way to prove it is to just unite all these points by a path like this, and then consider a path which goes around all of them and returns. So it would be a contractible path. It will be like this. So then express the integral here as sum of integrals over the points, and so on. So this is one proof. But in a way we'll be doing a similar thing. So proof. So at the point z equal aj, take the principal part of f at aj. So this means that we write f of z as sum of Laurent series. And then this Laurent series splits into two parts, which we called internal and external. So internal part was the holomorphic part, and external part was the principal part. So denoted by Pj of z, the principal part. So notice that f of z minus Pj of z has a removable singularity at z equal aj. So now consider the function which is the difference. So take maybe f, which is f minus sum of all Pj of z. So then it has removable singularities at each aj. So we killed the singular part of the function at each point by subtraction, like this. So then integral over gamma f is 0 by Cauchy integral theorem. So then we get that integral over gamma of f of z dz is sum of integrals over gamma Pj of z dz. So now we can modify this picture. I'll do it just on the blackboard. So we can make this path smaller. So if we're doing just one Pj, so Pj has singularity only at one of these points. So this is, say, aj. So we can ignore other points because Pj doesn't have singularity there. And now, as always, we consider the path, I mean the cut which connects the small circle around aj and this closed path gamma. And usual considerations with going like this shows that integral over gamma is expressible as integral over the disk. So yes. So R is whatever small enough. Oh, and then of course I get 1 over 2 pi r. Yeah. Oh, it's the other way around. Sorry, it's 2 pi. Yeah. So so this is 2 pi I. A residue of Pj and Aj. But we remember that f minus Pj has a removable singularity. residue of f at aj just equals residue of pj at aj. So now we just substitute. So now I'll erase so then I'll just continue this equality. So it's sum of these integrals, it's sum of integrals over d a j phi dj z dz. This is 2 pi I sum of residues of pj at aj. This is 2 pi I sum of residues of f at aj. So we started from integral of f over this loop and ended with this. But I think another way to argue with this, taking all these little circles together, would also work. Good. So now we'll apply this theorem, but before this, let's discuss technical issues. So calculating residues in simple cases. So, calculating integrals is not easy. Calculating Laurent power expansions is not easy, but sometimes you get a uniform formula which works without the whole expansion. So one such case is when h of z has a simple pole, so pole of degree 1. And z equals a. So so then so this means that h of z has the following expansion, and start from -1 to infinity, c n z minus a to the n. So, and we're interested in c minus 1. So how to get c minus 1 from this? So we take the function h of z times z minus a. And this is this has a removable singularity. So so it's expanded as sum n equals 0 to infinity, c n minus 1, z minus a to the n. So from this we see that c minus 1 is simply limit z tends to a h of z minus a. Now we can ignore this part. It was just an explanation, and just see that if we for some reason know that it's a simple pole, then we can get the residue like this. So example, in a way, it's a generalization of this. So suppose we have H, which is F divided by G, and F is homomorphic. F of A is not 0, G of A is 0, and G prime of A is not 0. So if you think about it, this corresponds to H being, well, the function, I mean, G being Z minus A. So I'm just emphasizing that B is a generalization of A. With G being Z minus A. Okay, so then let's see what we want to do. We want to calculate residue of H of Z at A. So you can write it in many ways, but just notice that it's a simple pole case. So then we take the limit Z tends to A of H of Z minus A. A, F of Z, G of Z, Z minus A, and now it's formal operations with limits. So this function has a limit at this point, so we can take it out of the bracket. Also, G of A is 0, so I can easily subtract G of A. Now, looking at this expression, we see that it's 1 over the expression for derivative. So then, this is and this is F of Z divided by F of A. F of A divided by G prime. Okay, so if you look in the book, then there'll be other examples when you can express residues without knowing series. But that's all I wanted to present on the blackboard. Now, I promised longer break for you to take the papers and to have a look at them. So maybe let's start now.